Our current model of the atom is one in which we have a dense nucleus that's composed of protons and neutrons. And because these protons and neutrons have much larger masses than the electron, they contribute primarily to the mass of the atom. The electrons, however, contained in a diffuse electron cloud which surrounds the atom, and this is mostly empty space. Because the electrons do not have much mass, they contribute very little to the mass of the atom, but contribute significantly to the overall radius or size of the atom. A complete description of an atom includes two parameters: the atomic number, which is abbreviated as Z, and this is the number of protons that are in the nucleus of the atom. In addition, we also look at the mass number, which is abbreviated A, and this is the number of protons plus the neutrons in the nucleus. So a full description of any atom will include three things: the atomic symbol, here generically represented as X, the atomic number Z, which is the number of protons in its nucleus, and the mass number A, which is the number of protons plus the number of neutrons. Now, all atoms of the same element will have the same number of protons. So I've given two examples on the right here. The first one is that of carbon-12. And you'll notice that I've represented it with its atomic symbol, C, 6 protons. Carbon has 6 protons in its nucleus, and in this case, 12 for 6 protons and 6 neutrons in its nucleus. There's another form of carbon, which is carbon-13, and carbon-13 is very similar, except that instead of having 6 neutrons, it has 7 neutrons in its nucleus. These two atoms are related in that they're both carbon atoms. They're different only in the number of neutrons that are in their nucleus. So atoms with the same element that have different number of neutrons are called isotopes. It's important to keep in mind that the carbon atoms shown here will be chemically very, very similar. They're indistinguishable. And if I gave you a sample of carbon, say in the form of graphite, the carbon that I gave you would be a mixture of carbon-12 and carbon-13, and you wouldn't be able to distinguish the two. You'll notice again that both carbon atoms, though, have the same number of protons, and this is because elements are defined by the number of protons in their nucleus. So just as another quick example, hydrogen has 3 forms, or 3 primary isotopes. There's hydrogen, which you're most familiar with, deuterium, and tritium. Now they are different in that they have different numbers of neutrons. Hydrogen has 0 neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. However, they all have only 1 proton in their nucleus, and the proton defines those different isotopes as being hydrogen atoms. The periodic table is in fact arranged according to increasing atomic number, so increasing protons in the nucleus. Hydrogen has 1, followed by helium, which has 2 protons, lithium with 3, beryllium 4, boron 5, and so forth. In addition, the elements in the periodic table are arranged according to types. Metals are in the left-hand side of the periodic table, here represented in green. Nonmetals in blue are on the right-hand side of the periodic table. And the semimetals are in a narrow stairway that divides the two metals and nonmetals. These different types of elements have different types of properties. Metals tend to be conductive to electricity and heat, and they tend to lose electrons very easily to form positive ions, whereas nonmetals are not conductive to electricity or heat, and they tend to gain electrons to form negatively charged ions, which we'll talk about in a later slide. In addition to these 3 main categories, you should be familiar with columns of elements, which are called groups, or families, and columns of elements tend to have very similar chemical properties. So for instance, lithium, sodium, potassium, rubidium are all metals with which tend to be soft and also tend to react very violently with water. The rows of elements are called periods because their chemical properties change gradually as you move from left to right in a sort of periodic fashion. Now, very few elements on the periodic table exist just as discrete atoms, except for the noble gases, so neon and argon and krypton. They will exist as single atoms, but most of the other elements, even in their pure form, exist as molecules. And molecules are atoms held together by chemical, in this case, since we're talking about nonmetals, covalent bonds. So for instance, pure hydrogen doesn't exist as just an H atom, but instead as H2, a diatomic hydrogen molecule. Nitrogen is very similar. Nitrogen doesn't exist in its pure form that you would breathe in the air around you as a nitrogen atom, but instead as a diatomic nitrogen molecule. And you can see that there's several other nonmetals that exist in diatomic form. Not all of the nonmetals are diatomic molecules, though. Pure sulfur, for instance, exists as these aggregates of S8 atoms, and pure phosphorus exists as P4, so 4 phosphorus atoms in this sort of tetrahedral type shape. Of the elements that were shown, though, most of them don't even exist in pure form, but instead react to form different types of compounds. So oxygen and nitrogen are commonly found pure elements in the air, but they can also react to form compounds. And there's 2 basic types of compounds that your book would like you to be familiar with at this point. There's molecular compounds and there's ionic compounds. Now, molecular compounds form when you have nonmetals react together. So as an example, I've shown 3 here. Here's carbon monoxide, which is made up of carbon and oxygen, methane, carbon and hydrogen, and nitrous oxide, which is N2O, which is shown here, which is nitrogen and oxygen. Now, nonmetals form molecules that are held together by covalent bonds, just like the pure elements, nitrogen and hydrogen and fluorine diatomics, were held together by covalent bonds. Ionic compounds, on the other hand, form in reactions between nonmetals with metals. And these are held together as ions by ionic bonding. Some examples are common table salt, sodium chloride, potassium nitrate, and magnesium chloride. Now, the difference between the molecular and ionic compounds is that while molecular compounds tend to have discrete molecules held together by covalent bonds, ionic compounds are ions held together in these large networks of ionic bonds. So these ions are held together by their opposite charges in a sort of a large network, which is why you have carbon monoxide, which is a gas under normal conditions, whereas sodium chloride, because it's a large aggregate of ions, is a solid. So let's define what an ion is. An ion is an atom or a group of atoms with a net positive or negative charge. So as an example, I have shown here a sodium with its diffuse electron cloud. Sodium has 11 protons in its nucleus, and since it's a neutral atom, it has 11 electrons in its outer shells. And here's its atomic symbol. If we remove 1 electron from this atom, we will have now only 10 electrons. So there's an imbalance. 11 protons, so 11 positive charges, and 10 electrons, 10 negative charges. That leaves a net positive charge on the sodium. And so the sodium has become called a sodium ion. a positively charged ion. We can also represent that in this equation showing sodium going to sodium plus an electron, and this is the electron that was removed from this sodium metal. We can also form negatively charged ions, and in this case we're using an example of fluorine. Here's our fluorine atom with its diffuse electron cloud of 9 electrons. It has 9 protons in its nucleus, so that's balanced, 9 and 9 for a neutral atom. However, if we add in an electron, now we have 10 electrons surrounding the atom with only 9 protons. So again, there's an imbalance. There's 10 negative charges, 9 positive charges for a net negative charge on the atom, and now this has become fluorine ion. We can represent that as fluorine plus an electron to make the fluorine ion F-. You'll also notice that when we added our electron to the atom, the size became larger. So whenever you add electrons to make negatively charged ions, you should see an increase in the size of the ion. Compared to our sodium example, in which sodium, the atom has more electrons, we remove electron and the ion shrinks in size due to the fewer number of electrons now that it contains. Simple ions are ions in which there's only one atom involved. And you should memorize all these simple ions that are shown on the periodic table and their charges. They're sort of grouped together, so memorizing them isn't too tough. For instance, all the 1A elements in this family have form positively +1 ions. The 2A elements, magnesium through barium, form +2 ions. And for instance, fluorine, chlorine, bromine, and iodine, the halides form -1 ions. You should also notice that the metals all form positively charged ions, and the nonmetals form negatively charged ions. And that's because metals tend to lose electrons, whereas nonmetals tend to take electrons or gain electrons. There are also polyatomic ions, and these are ions that contain more than one atom. And so, for instance, hydroxide ion is composed of an oxygen bound covalently to a hydrogen, and this whole entity, this whole molecule, has an extra electron giving it a negative charge. And there are several examples of these types of polyatomic ions shown. Your book has a table, and you should memorize the numbers of atoms and the charges of these polyatomic ions.